Standard planetary science relies on a specific sequence of events to explain the Moon's origin. The accepted model posits that approximately 4.5 billion years ago, a Mars-sized protoplanet designated Theia collided with the young Earth. The resulting debris disk then coalesced in orbit to form our lunar satellite. To test this hypothesis, we have to look at the rules of planetary accretion. In the early solar system, distinct planetary bodies formed in isolated regions, absorbing specific blends of nucleosynthite materials. This gives every planet and asteroid a unique isotopic fingerprint based on its distance from the Sun. Because Theia was an independent body that formed on its own trajectory, it possessed a distinct isotopic signature. If the Moon was formed primarily from Theia's destroyed mantle, the Moon must carry Theia's specific chemical fingerprint. During the Apollo missions, astronauts returned hundreds of pounds of lunar rock and regolith to Earth, providing the ultimate test for the giant impact theory. This chart shows the oxygen isotope offset of planetary bodies. Mars, which formed independently, shows an offset of roughly 320 parts per million relative to Earth. The lunar samples, however, reveal an offset of exactly 0. The Earth and the Moon are isotopically identical. This identicality holds true for refractory elements like titanium, which are highly resistant to vaporization and post-impact mixing. The lunar titanium isotope ratio is a perfect match to Earth's mantle, down to 4 parts per million. For an independent, Mars-sized impactor to possess the exact same oxygen and titanium isotopic makeup as the proto-Earth requires a degree of chemical fine-tuning that stochastic impact models struggle to produce. This total chemical identicality leaves the canonical model in a state of intractable contradiction, what researchers now call the isotopic crisis. If the Moon is not the resulting debris of a random collision with a foreign body, we are left with a central paradox. We must identify a mechanism capable of producing total identical homogenization between a planet and its satellite. The constraints of this paradox lead to an alternative framework, the Xenogenic Hypothesis, or Alien Vaporization Theory. This hypothesis defines the formation of the Earth-Moon system as an industrial-scale resource extraction event executed by an advanced intelligence. To test this, we evaluate the lunar geochemical record not as a natural phenomenon, but as a forensic crime scene. We look for signatures of artificial processing. The thermodynamic and chemical data are absolute. We have to follow those constraints, even if they model an engineered intervention rather than a natural accident. The first requirement is reproducing the identical isotope ratios. To completely homogenize the chemical signatures of a planetary body, you need extreme heat and massive, sustained energy inputs. In 2017, Planetary scientists proposed a theoretical structure that meets these requirements, known as a synestia, a rapidly spinning, donut-shaped mass of vaporized and molten rock. A targeted, highly energetic event could force the proto-Earth's rotation and temperature to spike, dissolving the mantle into a massive, expanding synestia. Inside this structure, the mantle transitions into a supercritical fluid. In this state, there are no distinct liquid or gas phases. The fluid dissolves solid materials and flows with zero resistance, like a highly dense gas. The internal temperature of this fluid torus reaches up to 6,000 degrees Fahrenheit. This extreme thermal gradient forces rapid, vigorous convection. The material churning through the structure is violently mixed in a very short time window. This supercritical mixing effectively erases any localized chemical variations. It perfectly equalizes oxygen and titanium isotopes across the entire mass, solving the isotopic crisis. A synestia is the only thermodynamic vessel capable of manufacturing the identical isotopic signatures we observe in the Earth and the Moon today. Once we understand how the isotopes were equalized, we must pivot from what is identical to what is missing. Lunar rocks exhibit a severe anomalous depletion of light, volatile elements. The Apollo data reveals specific fractionation patterns in volatile elements, specifically regarding zinc and potassium. Natural volcanic off-gassing on Earth releases light and heavy isotopes at relatively equal rates. High-energy vacuum vaporization, however, strips away lighter isotopes, while heavier isotopes selectively condense and fall back into the melt. This split-screen comparison shows how lunar data breaks from natural terrestrial processes. The Moon shows an extreme enrichment of heavy potassium isotopes, nearly 100 parts per thousand higher than expected. This specific fractionation pattern cannot happen by accident. It requires extreme, sustained heating in an absolute vacuum. Slow cooling accretion models in a debris disk do not produce this extreme bias. The physics dictate a rapid, high-temperature boil-off. The extreme bias toward heavy isotopes points toward a systematic and violent purge of the atmosphere, functioning effectively as an industrial off-gas. The vaporization of the volatiles sets up the final and most severe geochemical anomaly, the absence of core-building elements in the Moon. Highly siderophile elements, or HSEs, include metals like gold, platinum, and osmium. These are dense, rare, and possess a strong chemical affinity for iron. If the Moon condensed from the homogenized fluid of a synestia alongside the Earth, it should share Earth's concentration of highly siderophile elements. This chart compares the actual abundance of these elements. The lunar mantle is severely depleted. The concentration of gold, platinum, and osmium in the Moon is 20 times lower than in the Earth's mantle. Conventional models attempt to explain this through the late veneer theory, proposing that late-arriving meteorites delivered these metals to Earth after the Moon formed. But adding a massive volume of foreign meteorites to Earth violates the oxygen isotope identicality we established earlier. It also contradicts the precise tungsten-182 chronometry measured in the rocks. The math does not balance. This 20-fold depletion of heavy metals serves as the primary forensic marker of the Xenogenic Hypothesis. The valuable heavy metals did not sink to a lunar core that barely exists. They were extracted directly from the supercritical fluid. The data perfectly models an industrial siphon. The high-value elements were harvested from the synestia, leaving behind a sphere of depleted silicates. Once the extraction operation was completed, the synestia entered its cooling phase. The intense thermal energy dissipated, and the fluid condensed back into solid matter. The heavier harvested material collapsed to the center to reform the Earth. The discarded, volatile pore and metal-stripped silicates were left in orbit, accreting into the Moon. If this extraction occurred, evidence of the operation should still exist at the deepest levels of the modern Earth, down at the core mantle boundary. Seismologists identified two massive, dense anomalies resting against Earth's core, known as large, low-shear velocity provinces. Under the AVT model, their sharp density contrast and failure to integrate into the surrounding mantle marks them as solidified waste conduits, the sunken infrastructure of the extraction event itself. Under the AVT model, the Earth and Moon represent the final states of this operation, a processed resource cache and its corresponding slag heap. The forensic evidence rests on four pillars: identical oxygen and titanium isotopes, extreme heavy volatile fractionation, a 20-fold depletion of heavy metals, and non-integrated seismic core anomalies. To explain these four pillars using random celestial mechanics requires stringing together a sequence of statistical improbabilities, contradictory timelines, and chemical loopholes. The Xenogenic Hypothesis satisfies all thermodynamic requirements and matches the geochemical data with zero contradictions. The Moon's mass, composition, and location are the exact specifications of an industrial byproduct. True planetary forensics requires a strict adherence to the data. We have to accept where the thermodynamics point, even when the evidence reveals that we are living in an engineered solar system.